Hello, everybody. Today we're going to be revisiting particle motion. So remember in the fall when we did differentiation, we saw that velocity is a derivative of position and acceleration is a derivative of velocity. Now that we know how to integrate, we can work backwards. So if we have an acceleration function, we can integrate to find a velocity function. If we have velocity, we can integrate to find position. So the problems we're going to be looking at here will have some things in common with the problems that we did in the fall, like trying to figure out where's a particle turning and that sort of stuff. But we'll also have to integrate to work back up the chain. So let's just start with an example. So let's say we know a particle's velocity. So this particle is moving along the x-axis. If velocity is positive, it's moving to the right. If velocity is negative, it's moving to the left. Assuming that the particle begins at position 0. So the particle, when this time period starts, begins at the origin. Where is it after 5 seconds? So this is a question about position. We don't have a position function. We only have a velocity function. So in order to go from velocity to position, we want to integrate. So we know that position is the integral of velocity. So we just need to integrate t squared minus 3t. Go ahead and let you put that in play posit. T cubed over 3 minus 3t squared plus c. So here's where we're going to use the information about the particle's initial position. We know that when t is equal to 0, so initially the particle was at position 0, told us that in the problem. Excuse me. So we know that when we plug in 0 for t, we should get 0 out of the position function. So we're going to actually use that to solve for the value that c has to be. So in order for this to come out to be 0, c also has to be equal to 0, because we get 0 minus 0 plus c, and that means that c is equal to 0. So the position function that we get, p of t equals t cubed over 3, it doesn't look like a cubed, oops, minus 3t squared plus 0. So this is the position function. So to answer the question, where is the particle after 5 seconds, all we have to do is plug 5 into the position function. And you can go ahead and use your calculator. So when we plug in 5 and we put this in our calculator, we get that after 5 seconds, the particle is at negative 103rd meters. So it's 103rd meters to the left of the origin after 5 seconds. Okay, so then the second question says, assuming that the particle starts at position 0, where is it? So it's still a question about position when it's moving at minimum velocity. So we have two pieces of information we have to figure out here. We have to find out when is velocity at a minimum, and then plug in that time into the position function to answer the where. I'm going to erase this so that we can start answering this question. Okay, so we need to figure out when velocity is at a minimum. So anytime you see a question that says, when is blank at a minimum, you have to take the first derivative of that function and set it equal to 0. So we know that we want to solve for v prime. When I take the derivative of this, I get 2t minus 3. I'm going to set that first derivative equal to 0, so we're trying to find a turning point, a minimum, on the velocity function. We get that t star is equal to 3 halves. We do a sign chart here for v prime. If we plug in, let's say 0, we get a negative number. If we plug in 2 into v prime, we get a positive number. So because v prime is changing from negative to positive, that means that we have in fact found a minimum for velocity. So this particle has a minimum velocity at t equals 3/2. So then to answer the question that was asked in this problem, where is the particle at this time? And I'm just realizing I erased our position function. So we had a position function. Hang on one second. Okay, I got the position function back. To finish answering the question, now that we know that the minimum velocity happens at t equals 3/2, we just need to plug in 3/2 into the position function to find out where the particle is when that happens. So 3/2 is the same thing as 1.5, so I'm just going to use that. Okay, and we can just punch that in our calculator. Okay, when we punch that in the calculator, we get that the particle is at negative 2.25 meters when it is at its minimum velocity. Okay. So here's a problem for you to try. Here we're given an acceleration function, and we're going to assume that the initial velocity was negative 10 meters per second. So when at t equals 0, velocity is negative 10, and that the initial position was 0. And the question is, where is the particle after 7 seconds? So we have an acceleration function. We're going to have to integrate twice to get to a position function. So go ahead and first integrate a of t in order to find a velocity function. So we know that the velocity function is going to be the integral of this acceleration function. So go ahead and do that. Okay, we get that the velocity function is v of t equals t squared plus c. Now is where we're going to use the information about the initial velocity. So we know that initial velocity was negative 10. So when we plug in 0 into the velocity function, we should get negative 10 out. So we know that 0 squared plus c has to be equal to negative 10. That means c is going to be negative 10. So our final velocity function is going to be t squared minus 10. Okay. So we need to integrate this in order to get position function. So why don't you go ahead and do that and put your answer into PlayPosit. Okay, so I just integrated our velocity function. I got t cubed minus 10t plus c. Then I solve for c by using the information that was given about initial position. So we know that when t equals 0, position is also 0. So I plugged in 0 for t, set position equals 0, and so found out that c is also 0. So that's where we get our final position function there. And then to answer the question, where is the particle after 7 seconds? We just plug in 7 for t, and we can punch that in our calculator. Okay, p of 7 is 133 third meters. Okay. So here's another problem where you're given an acceleration function and some information about the initial velocity, initial position, and then we want to find its position at t equals 7. So that's identical to the problem that we just did. So for that part, up until here, why don't you go ahead and try that. I'll put in some questions on PlayPosit for you to put in your answers, and then we'll talk about the next question about distance traveled. Okay, here's the work to get the velocity function. So once you've got this, go ahead and move forward and integrate to a position function. Okay, here's the work for the position function. When I integrated the velocity function, I got t to the 4th minus t cubed plus 5/2 t squared plus 2t plus c. When you plug in the information about initial position, you find that c is 0. So here's our final position function, and I just plugged in 7 and put in a calculator, and got that after 7 seconds the particle is at negative 6.41667 meters. Okay, so the next part of the question we're supposed to answer is how far did the particle travel in between t equals 0 and t equals 6. So anytime you have a distance traveled question, and we've talked about this earlier this year, we need to be careful because we can't just integrate from 0 to 6, some of this area that we're looking at here on this graph. So this is a graph of this is a graph of the velocity function for this particle. So you can see at the beginning, velocity is positive, and then somewhere between 2 and 3 seconds, velocity changes to being negative. If we just integrated from 0 to 6, the area under the curve would start to cancel itself out once we got past the spot where velocity became negative. And so the end result would be that it would tell us where the particle was after 6 seconds, but it wouldn't tell us how far in total did the particle travel that whole time, because some of the time it was moving forward and some of the time it was moving backwards. So in order to find the total distance traveled, we have to break up the integral into 2 spots. So we're going to integrate from 0 up till this point, and you all can use your calculator. I'm just using Desmos, it's right here. Fascinating. The time where the velocity switches from positive to negative is 2.749. So I'm going to set up one integral and integrate the velocity from 0 to 2.749, and then I'm going to add a second integral that integrates from 2.749 up to 6, and that's going to give me the rest of the area. That'll turn out to be a negative number, but we'll just make it positive. Okay, so let's see if I can get back over to PowerPoint. Okay, so here are the 2 integrals I need to set up to answer this second question about the total distance traveled by the particle. This is just the velocity function that we got earlier. And we know if we integrate a velocity function, the area underneath it will be distance traveled. So we're going to integrate this first piece. I'm just going to put each of these in my calculator and see what number it spits out. So we'll post this up. Okay, so from the first integral, from t equals 0 to t equals 2.749, the particle traveled 8.375 meters to the right. And then for the other integral, going from 2.749 seconds to 6 seconds, the particle traveled 14.3753 meters to the left. So when you add those 2 numbers together, well, you need to make the negative one positive. When you do that and you add them together, you get that in total the particle traveled 22.7507 meters. So yeah, the moral of the story is anytime you have a question, you need to read the question carefully. If a question is asking where a particle is at any given time, you can just plug a number into the position function. If it asks you about a particle's total distance traveled, you need to really look at a graph of the velocity and see if there's any place where it switches from positive to negative. And if so, you're going to need to set up 2 integrals and add them together. All right. So we'll do some more practice problems in class, but that's a good overview of continuing particle motion. Thanks for listening.